Welcome to Purdue University College of Science Superheroes of Science podcast. I'm Stephen.
And I'm Sarah. We will be discussing anything and everything related to the science classroom and interviewing scientists.
Because as we know, scientists are the superheroes behind the science.
So join us as we learn about the scientists and explore current trends in K-12 science education. Today we have Professor Christina Li here with us. Christina is an assistant professor with the Department of Chemistry. So welcome. Thanks for being here.
Thank you.
Christina, how did you get interested in science?
I think I've been interested in science like forever, basically. I think there's something always just very appealing about science, and that it felt like there's always sort of a logical progression of ideas, and that I was sort of I liked looking at things in nature when I was a kid, and I liked logic puzzles. I liked things that were sort of like that made sense to me as a kid, and I was never that artistic and never totally understood how art came to be. But science seemed it's I could think it through. I could start at a point and I could get to the end and be like, oh, that all makes sense to me. And so I think I was pretty naturally drawn to science and to engineering and stuff like that. And so then when I was in high school, I did a bunch of the sort of science competition types of things. So Science Olympiad was my big thing when I was in high school, and I loved that because it was you would be asked to build a musical instrument out of random objects and understand something about the physics of how you made that thing, and I thought that was awesome. And
What ones did you compete in?
So I did that one. So the musical instrument that was called Sounds of Music, I think.
I think it was, yeah.
And then I actually did no chemistry events, even though I am now a chemist. I was sort of a random. I did astronomy. I did some of the ones where they're sort of identifying things. So I did one on birds where we had to just memorize. Yeah, we had to memorize the bird calls and what they look like and weird facts about them.
Okay.
Yeah.
Did you ever get thrown into some at the last minute because they need extra? I would say my kids have done
that
science
Olympiad,
and they'll just randomly, oh yeah, I also did. I'm like, you did what?
Yeah. It's it turns out I know nothing about this, but I'll do it. Well, there are some ones that I think were kind of general scientific skills. So there's one that was called, I think, Write It, Do It. I don't know where
I remember.
You have one person in a room that has to describe an object, and then the other person has to build it in the room next door. So that's yes, you can practice for that, and obviously you should, because you got to work out sort of communication with your partner, but you can also just kind of go in and do it and hope it works out okay. I feel I got thrown into that one once. And I did some of the building events, so the tower building ones, which were super fun because you're just sitting in your house gluing pieces of balsa wood together and then smashing it shortly thereafter.
Those are fun ones.
Yeah.
So you did Science Olympiad. You had science looked interesting. And so then what did you do?
So then I went to undergrad, and I think at that point I didn't actually know what type of science I wanted to do. I sort of knew that I liked chemistry, biology, but I was super undecided when I started college. So I took a little bit of everything. I took some computer science, I took physics, I took biology.
Wow, so you sort of saw a lot of different kinds of things.
And I think at the end of that, I was okay, I think I want to do sort of something in the chemistry or physics kind of range. So
so I narrow down your focus.
I think it was just what classes really appealed to me, and I'm sure some of that is colored by the professors that I had. Sure. If I had a great professor, I was excited about it and that sort of thing. But so I think around sort of sophomore year is when I was all right, I think chemistry is the thing. But actually, at Harvard they had these really weirdly named majors. So my major was actually called Chemical and Physical Biology, which is science. It's chemistry, physics, and biology.
Well, that kind of fit perfectly.
Yeah, and I was oh, this is sort of a weird name, but okay. But in reality, I would say I did mostly chemistry. So.
Okay.
Yeah.
So that was your bachelor's.
Yes.
You got that degree, and then what did you think you were going to do? Did you have a plan?
Yeah, I would say I probably, maybe around junior year was when I was okay, I think I could do grad school. Because I joined a research lab summer of my sophomore, so summer after my sophomore year. So I was working in a lab over the summer, and was like, oh, research is actually really fun. That they're sort of, I think like research can feel a little bit frustrating sometimes to people who are getting into research, but I think what I liked about it was like this sort of incremental progress. So it was like every day I was doing something and like making a new thing and like proving to someone that I made it and then like going on to the next step. So I was doing organic synthesis when I was an undergrad.
Oh,
Wow.
And that's like it's sort of just this process of like, okay, I know what my goal is, and like every day I'm gonna like try the next step and see if I can get closer to my goal. And that was like kind of satisfying. It can be like a little frustrating too, I think, but it was like you felt like you were making progress, and that you're sort of moving forward on a day-to-day basis. So I was like, okay, I think I could probably do this for 5 more years. That seems reasonable. I wouldn't say it was like a particularly profound realization, but I was like, oh yeah, I like doing this. Like I could do this some more, I think.
Well, I like that you're mentioning it got a little frustrating. And I know in the classroom when I would have students, I think sometimes they would complete a task or they would think something and then it would turn out they were wrong, or they would try something and it wouldn't work out quite how they had thought, and that can be very frustrating for students. So do you have any advice for students that maybe are kind of hit a wall and just think, oh, I thought I knew this and I don't, and I'm very frustrated, right? How did you get through?
I think for me it was more about sort of like the like small victories almost, that it's like yes, the big goal feels really far away often, especially when you're doing like lab research. You know, it's like, oh, my goal is to save the world, you know, or whatever. Or like make the next best cancer drug, or like solve the energy problem. And it's like, realistically, you're not going to do that as a student. And like even for me as a scientist, like realistically, I'm not going to do that in my career either, you know. But I think it's all about sort of setting sort of small goals for yourself and like taking sort of pride and joy in reaching those small goals, and like being excited, you know, about those little things too, not just about like, oh, I didn't make it to the big thing that I was trying to get to. But, you know, it's like, oh, I got this, at least like, you know, sort of in the context of my research, it would be like, oh, I got this like awesome, really pure product of this thing I made, you know, and like maybe it's not, that product was not that interesting in like the long run, but like I did it, you know, and that was an accomplishment for me in doing that.
I like that. I like setting small goals and feeling pride in those accomplishments. That's a good.
So what was, all right, so you decided graduate school would work, and so what did you go in for or as, or?
Yeah, so actually I took a year off in between undergraduate and graduate school, and I went to work in Germany for a year, which was awesome. I highly recommend this to anyone who is finishing undergraduate, or just like sort of in general, the idea of sort of taking a gap year I think is really, really great. Because I think especially in science and engineering, the path can feel very linear. It's sort of like, okay, here are the things I got to do, and it can like get a little bit plodding, you know, it's like people get burnt out, and you know, it's like they never get a chance to, I think, sort of like explore the world outside of their chosen path. But so I stayed in chemistry when I was working abroad, but I think just the experience of like, I was working in industry, which was different from what I had ever experienced. So I was working for Bayer, like the aspirin company. But in their crop science division. So they have like, you know, herbicide and pesticide business. So I was doing synthetic chemistry for them and making molecules and trying to discover new herbicides.
Wow.
But yeah, it was awesome. I was living in Frankfurt, Germany, and it was just like every weekend we would take the train to a different city in Germany and just go walk around and see what it was like, and it was just like an awesome experience. Wow. Yeah, so
okay, that's
that
cool.
was super cool.
Yeah.
Was there? Do you speak German, or was there some sort of language? Did you have to learn so much to be able to get by, or was it fairly easy?
It was pretty easy to get around. So I had only taken a year of German in college prior to going, so my German was extremely elementary. You know, I was like, "Hello, how are you?" You know, that sort of thing. But the company, so Bayer has an international internship program. And so they were specifically recruiting people from all over Europe, primarily. I was actually the only American there, but there were kids from England, from Spain, from France. And so actually sort of in our internship program, we all spoke English, like among each other. And then at work, we spoke kind of a mix. So my boss spoke excellent English. So he had studied abroad when he was studied, because he did his PhD in Canada or something.
Okay.
So he and I spoke English, but then with the other technicians in the lab, we would speak German, and sometimes I would just like throw in random English words because I couldn't figure out what I was supposed to say. But it was a pretty easy. It was like really easy to communicate and like get around. Like Germany is a very friendly country, I think, for English speakers. So.
Wow. Yeah, that sounds really fun.
So that was an internship, a 1 year internship.
1 year internship. Yeah.
Okay.
Yeah, it's actually, I think it's much more common in Europe to do like a pretty long internship, because a lot of the students I was with, they actually had requirements as part of their undergraduate. So like the French kids, I think, had to do like at least a 6-month internship before they were allowed to graduate.
Oh.
From
their undergraduate degree. So like everybody would just go out and go do a thing, take a whole semester plus a summer off.
Oh, working. That is an awesome idea.
Yeah, that they had these really like established sort of co-op programs that they were, and I think the British kids also had to do that. So yeah, so they were like on required school related things, and you can extend it to 1 year if you want to, I think.
Wow. That sounds like it'd be really valuable to just get out and see what other places are doing.
Right. Yeah, and it was actually really good because I think it sort of motivated me to come back to grad school as well, because like I love the experience of living there, but I would say the actual day-to-day work of being a technician, like a bachelor's level technician in a lab, wasn't that exciting to me. And so I was like, okay, yeah, there is a good reason to go and get a PhD.
Yes.
So where'd you go after your year? Where did you go to get your PhD?
I went to Stanford.
Okay.
And I decided kind of to switch fields. So I was in organic synthesis and decided, maybe I want to work on something a little different. So I ended up sort of in electrocatalysis was the sort of field I ended up in, which is a pretty different thing.
What exactly is that?
So we're primarily interested in thinking about sort of energy type catalysis. So how can we use electrons from electricity to drive chemical reactions? So normally I would say like in organic chemistry, we use chemical reagents of various types, right? So you got, one chemical reagent, you mix it with another chemical reagent, and ta-da, something happens.
I think that's what a lot of kids think of when they think chemistry.
Right.
They think, I'm mixing two things.
Right. So in electrochemistry, what we do is we take like a current. So you take some electricity from your plug and you stick it into your reaction, and you use those electrons to drive the chemistry that you're trying to do.
Oh, wow.
So, yeah, so thinking about sort of chemical reactions in a pretty different way.
And how does that apply? Well, how do you apply that? What's your end thing goal?
Yeah, so I mean, the main thing now is thinking about how we can build devices that use electricity rather than gasoline, let's say. So can we make a fuel cell that can drive a car? Or can we like take all of that, wind and solar energy that we're generating it and store it in some chemical fuel form so that then we can reuse it later and it's not just an intermittent source of energy. Because like right now we're generating lots of electrons, but we don't have great ways to sort of keep them around, right, when the sun's not shining or the wind's not blowing. And so we're trying to think about ways that we can take those electrons and sort of make them as useful as something like gasoline. So can we turn them into something that we can then store and transport and move around and then use them later on, hopefully, for some other process.
Oh, that is so cool.
That is. It sounds very timely for today. People thinking about different alternative fuels and things. That sounds really exciting.
It sounds like science fiction to me. I mean, that's like out of a movie.
But stuff like that already exists, right? Like we already have hydrogen fuel cells that are running cars, which is pretty cool.
Yes.
Not in this country yet, but in Japan they have Toyota's made a fuel cell car that they have like driving on the streets.
Oh, that's like on the streets.
Wow.
Oh, wow.
Yeah.
Not just on a test track.
Right. Yeah.
Oh, wow. I did not realize
I didn't realize that either.
All right, so for your graduate thing, what was it? Yeah, that's what you were studying, electrochemistry. And so was that your focus then? Where exactly were you?
Yeah, so in electrochemistry, you can imagine you're sending electrons into a chemical reaction, but you can react it with lots of different things, right? So for example, if you were trying to do hydrogen fuel cells, you would be reacting it with water to make hydrogen. So we're trying to use sort of benign things, right, that you can convert back and forth without generating additional carbon dioxide. So in my case, what I was trying to do actually was trying to recycle carbon dioxide. So I was trying to take those electrons and send them into CO2 and try to turn it back into something that we could use as a fuel. So like a recycling scheme. So if we could take that waste CO2 and potentially turn it back into something like ethanol, right, which we blend into our gasoline and stuff like that, and then we can reuse it, and then we never sort of emit it out into the atmosphere. We just sort of, as soon as we produce it, we cycle it back into our recycling machine, turn it back into ethanol, and then it becomes a closed cycle for CO2. So that was what I was working on as a graduate student.
And so your official PhD title was, did you when you did grad school, was it a master's and PhD together?
It was,
or was it two
PhD
separate places?
only.
Oh, okay.
Which is pretty common in chemistry, that most students are sort of enrolled as PhD students here as well, where they come in, most of them come in without masters. A few of them will have a master's first, but most people come in straight out of bachelor's, and they can take a master's if they wish. So if they decide, yeah, maybe I don't want to finish the PhD, it's not for me, you can get a master's after 2 years. Or if you go all the way, then you just get the PhD at the end.
Okay.
So that's what I did.
What would the length of that be? So a master's roughly 2 years, and then if you go,
PhD about 5 years in total.
So what are you doing here at Purdue then? What are you researching and looking at?
Yes.
That you can tell us. No like trade secrets.
No trade secrets.
Are you doing like a flux capacitor, like Back to the Future?
Well, if I was, I couldn't tell you about it. So I'm working on stuff that's pretty related to what I was doing during my PhD. So I'm really interested in thinking about sort of more efficient ways to convert electricity to chemicals and vice versa. So it's all about sort of energy conversion, right? Can we take one form of energy and turn it into a different form of energy so that we can do stuff with it and then turn it back into the same form maybe that we started with before. But I would say that sort of specifically now we're in the field of sort of catalyst design. So we're really interested in developing the catalysts that can accelerate these reactions. Because if you just, stick some electricity into a vat of water, nothing really is going to happen. So you need to have something that sort of helps push that reaction along.
Okay.
And so we're trying to design those catalysts that can sort of make those reactions more efficient, make them faster, make it so that, it's cheap enough to put it into a car, that sort of thing.
What are some materials for the research that you're doing that work well as catalysts? I know catalyst is something that we would talk about a lot in high school chemistry, so I think that's a great key word here that they would know and recognize.
Yeah, so a lot of the best catalysts for electrochemical reactions are super expensive. So we use things like platinum and palladium very commonly. And so obviously that's going to be tough to commercialize on a really large scale, right? If you're talking about transforming, all of the electricity grid into something that's going to run on hydrogen, we're gonna have to make that way cheaper than it is right now. So one of the things that we've been interested in is thinking about how to make your catalyst contain less platinum. So we're still using platinum as the catalyst, but we're building up these sort of complex nanoparticles that have something else in the center that's cheap, like nickel or iron or something, and then we just put this super thin layer of platinum out on the surface so that the platinum is still doing most of the work, but we've got the central core that's sort of holding it all together made of something else. So that's one of the things we've been looking at, is just like developing the synthetic strategy to do these ultra thin coatings that are still stable and reactive and will still do the chemistry we want it to do.
Thank you for explaining that. That's cool.
So she's like the new and improved Tony Stark. She's Iron Woman instead of Iron Man.
But I don't have a suit.
The new energy. Well, you're working on how to energize that suit first, right? Then we got to get you a suit. Yes. And so in 50 to 100 years from now, where do you foresee this being? I mean, will we have a flux capacitor? Will we be able to do whatever that thing is Tony Stark has in his chest to power an entire super suit?
Right. I mean, I think that it seems likely to me that we're going to move away from fossil fuels. And I think the question now is what alternative fuel we're going to choose. And I think that's sort of a really active area of research still. that there are some technologies, things like hydrogen, that are a little bit more well established. There are obviously batteries that are well established. But I think the question is sort of what's going to be cheap enough and scalable enough to sort of take over our entire grid, right? Because right now we use an enormous amount of fossil fuels, right? So is there something that can actually replace those fuel sources? Because right now all of the sort of electricity type applications are like little things, like your phone or something, right? And like your phone is a really high value object, right? It's expensive, so you can sort of afford to put a fancy battery in there to do the job it needs to do. But like if we're talking, you know, the things that run all the lights in our buildings, right? Like, can we afford to put a 10,000 fancy batteries like in a row to make that happen, right? Because you only need one or two to run your phone. So I think there's still sort of an open question. Like, there are people who are researching cheaper batteries, right? Can we make the battery cheap enough that if we have, you know, hundreds of thousands of them just in every single building in the world, like, is that going to be a viable option? And then there are people researching things like hydrogen fuels that, you know, you can renewably generate the fuel. There are people researching things like CO2 reduction. Can we recycle carbon-based fuels and turn them into something we can reuse? And so I think that's the question that sort of the field in chemistry and engineering is trying to answer right now, because it's like it's coming. We just don't know in what form yet. So
we had some students visit campus, I think it was last year, and you had a really neat question for them. I was just reminded of this when you said our phone can use one or two of those batteries, and you had asked them, how many batteries do you think it would take to operate a vehicle? Is that right?
Yeah.
So
it's a lot.
How many? Right, I would think. I don't know what I would guess. How many batteries would it take right now to operate roughly? You know, just your general run of the mill 4-door.
Yeah, I mean the Tesla, it's like 10,000
batteries.
Lithium ion batteries. So like phone-sized batteries hooked up together.
It'd be like 10,000 of them.
10,000.
Oh wow, it costs enough to replace the one on my phone. I can't imagine that.
Yeah, I mean, I think that's also a huge open question, right? Because like Teslas haven't been around for that long yet, and so they haven't quite gotten to the point where people are going to have to like replace their entire battery pack, and like, is that going to be viable? You know, because that's also like an insane amount of money to replace that battery pack. But yeah, it's kind of a weird thing. That's like basically they've, you know, replaced the fuel tank, like all of the things that are in your normal car. They just have this huge like battery pack sitting in the bottom now.
So you think eventually we'll get to the point where those are affordable for the masses per se?
Well, I think it depends. I don't know that sort of lithium-ion battery cars are going to be the default state for the future. I think that's the best technology right now, because a ton of work has gone into developing lithium-ion batteries for sort of laptop and phone type applications. The question is there like a new generation battery that's going to be better? You know, it's going to be cheaper, it's going to be more stable,
maybe
smaller, less heavy, right? Because it's also like a huge weight on the car, the lithium-ion battery. Because I think that is the most expensive part, I think, as well, of the car is the battery, and so we're gonna need better stuff, right? If everyone's gonna be driving an electric car.
So we know about the science you. What about the personal you? What do you enjoy doing? Next week you're gonna take vacation and unwind and relax, and what are you gonna do?
Yeah.
I know it's theoretical. You never really get to take vacations, but you know.
I would say that I had an extremely balanced life when I was in graduate school, and I have a less balanced life now as an assistant professor. When I was in grad school, actually, I played a lot of ultimate Frisbee. That was one of the things I spent a lot of time doing. I played on the Stanford team as a graduate student, which was really fun. I was always like the team mom because I was like 10 years older than the freshmen. Not quite 10, but nearly. They thought I was super old. They were like, "You were born in the 80s?" And I was like, "Indeed, I was." But it was fun. Like, so we would like travel together and stuff, and we go play tournaments. That was great.
That's awesome.
I a good amount of classical music. So I play the piano and I play the flute. So back in college and grad school, I played a lot more. So I would play in orchestras and chamber music ensembles and stuff. And now, less so. I play by myself at home every now and again, but not super often.
I've never seen Ultimate Frisbee before until this summer, and I was able to see it. They were having some sort of tournament here in the middle of Lafayette, and,
cool.
And it was neat to see. I'd never seen it.
It's really fun.
I've never seen it, so I'm trying to envision in my head how a competition would work.
I would say that it's kind of a cross between like soccer and football in terms of how the rules work.
Okay.
So you have there are two end zones on either side, and like the team line up on the two end zones, and then you do kind of a kickoff, but you throw it, obviously.
Okay.
And then the goal is just to march all the way down the field and get it into the opposing end zone. And you can't run with the Frisbee, so you have to throw it, and that's like really the only rule. But they're like well-developed like offenses and defenses and like plays that you can run and like all kinds of stuff. It's pretty great.
I had no idea.
I feel like I'm really missing out on life here. This sounds so fun. Well, we appreciate chatting with you this morning, and thank you for explaining your research and how you got where you are today at Purdue.
Yeah, for sure.
Thank you for listening to our podcast.
If you love Superheroes of Science, be sure to subscribe, rate, and give a review on iTunes or your preferred podcast player. Be sure to join us as we add interviews of scientists and incorporate discussions of current trends in K-12 science.
Until next time, be super, and remember, you are someone's hero. Boiler up.
Hammer down.